Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, let's learn a little something about transformations of function graphs. Now, if you're with me and you've been following my series on volume and surface area and such, that was a geometric concept. We're past it now. We're going back to some algebra stuff. If you've been following me on the absolute value train, what we've been doing with vertex form, then you're in a pretty good position here in looking at the transformations of function graphs of any kind. They don't have to be absolute values. Later I'll get into quadratics with my specific integrated math 2 class on just how to graph those in a way. And you're going to see a couple quadratics here as well. If you've done it before, then it should look a little familiar at the end. As I do, I believe, I think it's 16 practice problems, and the last two at the end will look at quadratics in such a way where you take that parent function x squared and do something with it. But we're going to be doing the same thing here. We're going to take graphs and we're going to translate them, move them left, right, up, down. We're going to vertically stretch or compress, horizontally stretch or compress them, and perhaps flip them over, all depending on the nature of the graph itself. Now, a lot of these graphs won't actually have the equation revealed to you in any sort of way. It's not necessarily about what the equation is. It's like hidden in a black box of this function called f of x. And we're going to transform it in a way called g of x. The transformation will be described or written as an equation. And we're going to go ahead and do that. So, if you look at this problem set right here, we're going to get a bunch of graphs. There's going to be a description on each one asking us what to do. Just one thing at a time, I believe. It's one thing at a time. And we're going to make sure that we can make sense of them in the equations. And then on the later pages here, we're going to talk about odd and even functions. I'll get into that. And at the very end, we'll do several transformations in one. Several transformations in one in such a way that, we do just more than a single translation or a single stretch or whatever. We possibly reflect and translate and things at the same time. So let's go ahead and get started. And for you to make the best sense of this, guys, when they talk about write g of x in terms of f of x after performing the given transformation of the graph of f of x, we're going to say, okay, g of x is some new version of f of x. We're going to transform f of x in such a way. Instead of just taking f of x here, we're going to possibly have a vertical stretch or compression. We might possibly flip it over using the value a. And if you've seen a before, you're going to see it again here. That's how it's going to work. There's also a value called b. This part gets a little confusing, and there's this 1 over b portion. I don't know if I'm going to dive too deep into the why of the matter, but 1 over b is inside the function in and of itself, and multiplying by this x minus h. If you've been around for any sort of graphing stuff with transformations, you've probably dealt with this part before. The 1 over b is a little bit weird. It has to do with horizontal stretches and compressions. We'll get into that. The h has to do with a horizontal translation, k with a vertical translation, up, down. This is that general form. We're taking this f of x, we're possibly horizontally and vertically translating it, horizontally and vertically stretching it or compressing it and flipping it over from its original state, and then we get something else out. Now, in its default form, y'all, we got a being 1, because if a was 1 times that thing is just nothing. B being 1 in the same reason. 1 over 1 is just 1 times this is just nothing. Or, it leaves it unchanged. H as 0, subtracting 0 leaves you with just x. And k being 0, adding 0 to this leaves it unaffected as well. So by default, these are the values that we assume in such a way that it would be left to say g of x equals f of x, that they'd be the same thing if these were just 1, 1, 0, 0. But if any of these change, there's a new appearance in the graph, and that's what, or in the equation, and that's what we're going to be doing with that. And of course, we're going to be graphing the result. So keep this one in memory here. I'm going to go up to it every so often to show you what it looks like. If you've done enough of these, if you've done the absolute value functions with me, you've seen a, h, and k, just like this. You've dealt with the translations and the vertical stretch factor. You haven't dealt with b. There are a lot of times where, well, you know what? I did deal with b, but what I did was I transfused it in with a. I made a new a out of the b that was there. And a lot of different function types you can do that. Absolute values being one of them. Quadratics being another. I wouldn't probably dare do it with some other kinds, but there are some where you can, and it's good. So anyway, they want us to write a new equation in this form here after doing the given transformation. And like I said, it's only one transformation at a time. And I will also be changing the graph with it so you see exactly what this means. So here we go. Let's go and get started. Let's see this equation thing for what it is. I'll probably drag it down with it so you can always see it with us. On number 1, we're going to translate this graph of f of x to the left 3 units. So translate means just pick it up and move it. You aren't going to reorient it like a rotation or anything else. I'm basically going to have this graph right here, this graph that you see, but instead it's going to be it's going to be moved 3 units to the left. So ultimately it's going to look like 1, 2, 3, and this would be your g of x equation. If this was f of x, this would be g of x. Now there's a way of writing this equation in terms of f of x. That means f of x is a part of the equation, and you might not know what this equation actually is. I actually happen to, just because I know how semicircles are, because this is a semicircle, I know how they're graphed and how they're made. That's irrelevant. The point is they gave you a function, they call it f of x, let's use it and let's do the transformations. So this goes to the left 3 units. Now what that means is this is regarding h. Let me kind of write some of these things here. This is a horizontal translation. H is a horizontal translation. So with h there, h is -3. I say negative because it's said to the left. As we horizontally translate, to the right would be positive, to the left would be negative, with h being a -3. Assuming that a and b were still 1 and k was still 0, I can rewrite this equation here. Let me give you kind of the raw version, the raw form here, just so you know what I mean by the things going away. This equation would look like this. G of x equals, a would be 1 because we didn't vertically stretch, compress, or reflect. We'll multiply this by f of the b is 1 over 1, no vertical. No horizontal stretch or compression here, no vertical stretch or compression here. And then x minus -3, and then plus 0. That's the raw form of this thing. And I know that looks very confusing. So what's going to happen here is I'm going to clean a bunch of this stuff up. G of x equals 1 times all this is just that f of something. 1 over 1 is just 1, and 1 times this is just that part. So I'm going to be left with x minus -3. Subtracting a negative becomes addition. That becomes x plus 3. And then plus 0 is, you leave that out. So the final result of this is g of x equals f of x plus 3. Whatever f of x was, which it's a radical equation. It's a square root one. Whatever f of x was, instead of plugging x into the things, you plug x plus 3 into it, and you get this appearance of this thing right here. It's a brand new equation. That's what it looks like. And that's what you're going to do. You're going to write the equation. You're going to graph the thing based on the result, and that's what we get. So that's number 1. Number 2, translate the graph of f of x up 2 units. So up is in reference to k, and positive value, if you will, k being 2. K is with respect, or k represents the vertical translations. So this is a vertical translation of k here. So with k equaling 2, going up 2 units, I should say, we're going to take everything. Let me just do 1 point at a time. Go up 2 units here, go up 2 units here, and then go up 2 units there. And you have kind of this new looking semicircle that goes like this. I don't know how many, are all these semicircles here? Nope. Excuse me. So this is your g of x, given that this was your f of x, the original function. Now, what does the equation look like? Now, a and b being 1, h is 0, k is now going to be 2. So taking this equation here, again, these kind of go away. We have g of x. The new graph g of x is the same as f of x, but you know what? Everything is 2 units higher. Add 2 plus k plus 2. That goes on the outside there. That's what that one looks like. That's the equation after you transform it. Okay, number 3. Number 3 represents to me what looks a little bit like a cubic function if it kept going. Like, cubic functions can have the power to do that there. Translate the graph of f of x to the right 4 units. So this goes back to the h idea again. This time it looks like h would be 4. And this is fun. You know what? H is 4. So h is 4 this time. So the same kind of thing here. I get to take each point 1, 2, 3, 4. Look, it lands on that one. This original point that was behind it. 1, 2, 3, 4. And I can grab some of these height points right here. I don't know if they're hitting exactly at those spots, but close enough. 1, 2, 3, 4. Kind of there-ish. And this one's a little on the left there. 1, 2, 3, 4. I don't know if it's supposed to be perfectly on those values. I assume not. But getting this graph here. Oh, look, it connects. That's nice. That's pretty cool. So it translates to the right 4 units there. And that's what g of x looks like here, where f of x is here. Now the equation if you remember the form, it's the x minus h. So minus h is now minus 4. That's g of x equals f of the quantity x minus 4, like that. And that's the only thing that changes. Once again, there was no stretch or compression yet. The first 4 problems look like they're all translations, and then we go into some other ones. All right, number 4, translate the graph of f of x down 3 units. Now that we're going down, well, that's k, but down is negative, so k is negative 3. So take this same kind of graph. Let's go down 1, 2, 3. 1, 2, 3. This point 1, 2, 3. And this point 1, 2, 3, like that. And try and connect those dots, give yourself a g of x. Looks like these will not connect here. Not as pretty looking of a graph as my first one, but that's okay. There's my g of x, and we already know that's g of x, the other's f of x. But what is the equation? That's the part we do not know. Negative 3, we are going to be adding k at the end after the f of x bit. We're adding a negative 3. That means we are subtracting 3. So this is going to say g of x equals f of x minus 3. And remember, or well, if you don't know, or just as a recollection, f of x and g of x are other ways to say y, to say like the letter y, like x and y. They're to give you 2 different y values at the same time, or 2 different y equations. So you can have y equals this for f of x, and then y equals this for g of x, and we're taking one of the expressions and we're transmutating it, or transforming it. So the idea of this is these y values will be whatever these y values were, but 3 less, 3 lower. We'll take whatever this y value is, subtract 3 from it. What are these y values? And that's kind of how the equation's being represented. All right, let's get into stretch factors, horizontal stretch factors and vertical stretch factors. And honestly, the horizontal stretch factors are a little bit crazier because they use this b value that's not only within your function bit, but it also is written as a fraction. And I didn't mention, and you probably ask at some point here, and you'll be asking here, why are we dividing by b? But even furthermore, why were we subtracting h? If you notice, k was added, h is subtracted. Was there something specific to that? Sort of, it's not going to be a deep talk about it, but if k has to do with vertical stuff, and if this is all about y here, k and y are on opposite sides of the equation. That has something to do with it. H and x are on the same side of the equation. So, if k was on this side of the equation, it would say minus k, y minus k. So, there is a reason why one is subtracted, the other isn't. But really, why is it subtracted? Why are we taking the opposite? Because it's not about h. You have to remember, this thing's all about x. It's asking what are we plugging in for x in order to mimic that of the f of x thing. So you're taking the opposite thing. I can't get really too deep into it, but that's gonna be the same thing with b. We're asking what do I have to plug in for x so that it cancels out how b is affecting it. If I'm dividing by b, then I need to make something b times larger in x on the graph, and that's why we're dividing by b, but we're multiplying by a, because a is on the outside. But okay, let's go ahead into this. Number 5, stretch the graph of f of x horizontally by a factor of 3. Horizontal stretch factors in reference to b because it is a stretch by a factor of 3. B equaling 3 means we are going to take it and widen it out here. Everything's going to be 3 times larger in x for whatever x values that we do have. The y values stay the same. So this is x equals 2. Let's triple x equals 2. That gets us 6 right here. Let's triple x equals negative 2. That gets us negative 6. And the only for sure distinct point the only other distinct point I can get is this one, and I'll just use a semicircle. But this is x equals 0, so it's going to stay right there. It doesn't move, and we still have a semicircle here, but it's going to be a heck of a lot more stretched out. And pardon me for not having probably a perfect looking semicircle here that I'm going to attempt to go for. But alas, we still have one that is horizontally stretched by a factor of 3. Now that equation will look like this. It'll look like g of x equals, so a is 1, so this is just f of, and then, there was the 1/3, there's the 1 over b. So now b is 3, this will be 1/3, 1 over 3. And if this had some x minus h thing, I would put it in parentheses there. But there is no minus h aspect, as h is just 0. I can happily put 1/3 x inside there, and that's fine. And then plus k plus 0 right there. That would be your final result of this thing. And again, b is not a heavy talk. of some functions, absolute value functions, I'm able to get this b factored out of the absolute value, and I can work with that and talk about it more in terms of the vertical stretch factor. But with respect to what we have, we don't know what kind of function this is. I'll put the b value inside there. And just to kind of make sense of this one more time, guys, let's make sense of what it is that we're saying here. Why is this b the 1/3? Well, let's talk about g of 6. G of 6 meaning what is the value of y when x equals 6? Well, g of 6, guys, we can tell is 0. When x is 6, y is 0 on g. But what we're asking is, where can we get the same y value on g with f? And the answer is we can get that at f of, what's 1/3 of 6? 2. 2. Here's g of 6, here's f of 2. They have the same y value. I have to triple my x value on g to match the equivalent y value that you have here. That's why the 1/3 is there, and we're talking about x. We do a horizontal stretch factor, but we say that x had to be tripled here to make that happen. And that's the end goal. Remember, these are both y's. We get the same y here, 0 equals 0 for both of those. Kind of fun. Probably going over long on that. I just wanted to teach that so you're not just mindlessly plugging something in, but alas, that kind of also is what we're doing at the same time. All right, stretch the graph of f of x vertically by a factor of 2. Vertically, a vertical stretch is a equaling 2 here. This is something you'll see more often when just naturally with these graphs here. So let's stretch everything by a factor of 2. This has to do with y values here. So this y value is 0, so when I multiply it by 2, I still get 0. Nothing really stretches at this one individual point. Same with this one right here. But these points are right there on the graph, right here and right here. What is distinctly stretched is this 2. By a factor of 2, it gets doubled. This becomes 4 right there. And this becomes, it goes from a semicircle to a semi-ellipse. Number 5 was the same. It goes into semi-ellipse right there. That is stretched out, whoa, like that right there. And that's the appearance of the graph. Now with a being 2, that's the number in front of f right there. So the g of x here, we double whatever the f of x values were, whatever the y values were at certain x values, now they get doubled. Including all these ones here. They're just not distinct points, and I'm not going to find a way to really plot them very well. Let's thicken that thing out. That's your g of x. All right, let's go ahead and keep moving. Let's go number 7 and 8. Now we have a compression. Compression by a factor of 1/3 horizontally, compression by a factor of 1/2 vertically on these what look like absolute value functions here. This just looks like the absolute value of x. But we're just calling it f of x. We're not assuming to know that. So this is horizontally. This gives you a b value of 1/3 right here. Now, compressing horizontally, that means squishing in this way by a factor of 1/3. So in this case here, we have to take whatever x values are and take 1/3 of them. I'd rather only do x values where I can take 1/3 and happily get an integer. So taking 1/3 of 1 gets me 1/3. I don't really want to plot that point. 1/3 of 2, no. 1/3 of 3, yeah, that sounds good. Or negative 3. 1/3 of negative 3, divide that, you get negative 1. Right? I'm taking 1/3 of the x values. I'm compressing it horizontally, squishing it this way. Same with this side. 1/3 of 3 is positive 1, so I get that one right there. 1/3 of 0, by the way, is 0, so that's going to stay there. And then what? Go up to 6. 1/3 of 6 is 2. 6 divided by 3 is 2. And negative 6 divided by 3 is negative 2. So you can see this horizontal compression. This graph doesn't get taller. If you look back at the previous graphs that we just did, you know, these domains are infinite. So what we're doing is we're saying, I mean, I guess it does get taller, but remember, they're infinite. What it says that these, to achieve the same y value, you have to be 1/3 closer to the y-axis, I guess, on x to make that happen. Now, the equation, here's the raw form of it. G of x equals, it's f of 1 over 1/3 x, right? Your b value is 1/3. So we have 1 divided by 1/3. That is its raw form. But dividing by a fraction means multiplying by its reciprocal. 1 divided by 1/3 is the same as 1 times 3 over 1, or just 3. So dividing by a fraction there, you don't want to leave it like this. Instead, we're going to turn it into f of 3x, like that. And remember, this is a little misleading just because this is a 3. We do actually compress that thing. Now, there's a bit of a controversy here, and I can't explain it very well, but you know, notice that it did say compress, which means shrink it, and it says by a factor of 1/3. It almost seems like a double negative, right? Just like when I said dividing by 1/3 doesn't mean you divide it by 3, it means you multiply by 3. So we just say compress out of courtesy. You know, if I said stretch by a factor of 1/3, I guess technically I still mean the same thing. It will compress because the number is 1/3. So when I say compress, I don't mean like division, if you will. I'm just giving you a courtesy call of it will shrink horizontally in some sort of way, but the 1/3 is still a 1/3. So just kind of letting you know we're using this word as a courtesy, but it's this number that really does matter. And horizontally means it's B. Vertically right here means it's A. We're going to compress by a factor of 1/2. Again, if this had stretch, it's still a 1/2. That's the only thing that matters. It technically does not stretch. It does compress. But this 1/2 here, you know, there are a couple ways to look at it, but to make sense of what we did here, I'll take half of my Y values here because it's a vertical one. So half of 1 is 1/2. I don't really want to plot that. Half of 2 is 1. Plot that. Half of 4 is 2. Half of 6 is 3. Half of 0 is 0, and we can go the other way on this. Half of negative, it's still 1. Half of 2 is 1. Half of 4 is 2, and half of 6 is 3. So an absolute value function here that is now vertically compressed by a factor of 1/2 looks like that. If you worked on the absolute value function things with me, I did mention that absolute value functions have a constant rate of change. That means you can almost treat it like a slope. That A being 1/2 does kind of mean like an up 1 over 2 thing. Up 1 over 2, up 1 over 2. I wouldn't focus so much on that though, because it's the only one that does do that. Because it's the only one that's linear of these complex functions. But you do kind of have a 1/2 thing going there. Now the equation with A being 1/2 is g of x equals 1/2 times f of x. And I don't dare do anything different with that. I call it one. Well, actually, you know, I could. I could call it f of x over 2. I could say this is f of x divided by 2. Either or. I do prefer this one. I like seeing the a value for what it is in front based on the equation things that we have. But there's nothing wrong with that answer either. I probably wouldn't put 0.5. Okay, reflections. The last 4 as far as these graph bits. Reflect the graph of f of x across the y-axis. Now the y-axis is this guy right here. That's your y-axis. And a reflection means taking this thing and flipping it over. So this thing looks into the mirror and flips over here. This thing looks into the mirror and flips over here. Everything's going to flip over this way. I know this thing's vertical here, but this is the mirror that it's looking into and flipping around. I can literally, because I'm on a computer with this software, I can literally take this drawing and actually reflect it first. I'll show you what that looks like, and then I'll go back and get the individual points. But I just want to get you the idea or the concept of these reflections in a nutshell. So if I take this object right here, this blue one, I'm going to go ahead and I'm going to flip this way. And this is what we're going to get. This is a reflection of it. And you can see that symmetry with the original f of x and the new g of x here. We flipped across the y-axis, so we flipped, I know it says y, but we flipped horizontally, left to right. And when we talk about horizontal flips, we are talking about b, the b value. It didn't stretch or compress, but it flipped. It reflected. It went in an opposite direction. And for b being an opposite value, we're referring to a b value of a negative b value. B, in this case, when we do this, it'll be negative. And it'll be -1 because they didn't mention anything else about a stretch or compression. Now, as far as graphing it, you just saw it here. But this point, what was +2, when it reflects across the y-axis becomes -2. I'm talking about the x values. The y value stays the same. Over here, what was a -2 flips to become +2. This point up here that's around kind of like -1-ish will flip over here and become like +1-ish. And then this one will flip over there on that side like that. So you are going to get that graph that I did just draw before, only now we'll... Oh, and 0. 0, by the way, stays at 0 right there. So those should intersect together in that kind of way. So there's the graph. There's the b. And let's go ahead and write an equation out of that. That'll be g of x equals... Now, the b is inside there, right? This is f of 1 over -1 x. Now, 1 divided by -1 is -1. And -1 times x is just -x. So g of x is f of -x. This isn't the first time you're going to see f of -x today, by the way. You're going to see something else with this. And how it flipped and maintained some stuff. So that is the new version of that, writing it out in the value. All right, number 10. Reflect the graph of f of x across the x-axis. So now we're going to be looking across this one right here. It's not the same graph. It's an absolute value function. And we're going to take everything and flip it over down this way. The graph will be, if this is a V, the new graph will be an upside down V. So every point that we have here, the x's stay the same as we reflect across the x-axis. The y values are the ones that change. We take the opposite signs of them. So 0, 0 stays the same right there. But this y of positive 1 becomes a negative 1 there, and positive 2 becomes a negative 2 there. We maintain the x values as we change these right here. And you can kind of see this is just a down 1 over 1 kind of graph right there as it reflects across. And the same thing on this side. Down 1 over 1 this way as it reflects across there. And you, ultimately, it looks like we're going to get a big X. I'm sorry, let me do the arrow version here. Solid arrow. There we go. That's the graph of your g of x right here after this reflection across the x-axis. Now across the x-axis, remember it did go downward. That's a vertical reflection. That's in reference to a. The a value is negative 1 at this time. They didn't mention a stretch, so that it's still a 1, but it's negative. So this is going to be g of x equals negative 1 times f of x, or just negative f of x. Whatever the y values were here, we're going to take the opposite of them, and that's how the g values are going to work. That's what that means. Okay, 2 more with reflections across both axes, y-axis and x-axis. I don't think I have to get too deep into them this time, so I'm just going to go ahead. I'll give you that axis of symmetry one more time here. Here's the y-axis, and we flip it over the y-axis so it flips left-right. So this point stays the same. This point flips over to positive 3, and I get another part of a quarter circle, a little piece of that arc right there. It's actually not badly drawn. Because it's a left-right, that's a b value. That's a b of, once again, negative 1 as we reflect across that thing. So this will be just like the last one. It's a new kind of f of x graph, right? It's a new function, but we don't know anything about it as we just write this, just f of negative x. It's still that same answer there. That doesn't change. It's just a new f of x, what we do with it. Lastly, number 12 here, reflect across the x-axis. Right here, we are going to go downward in such a... Ooh, I had these arrows here. That's a big my bad. There we go. All right, so reflect across the x-axis here. This point stays the same, but this one goes down vertically. That's in reference to a there. We complete the quarter circle right here. Once again, not terribly drawn. So that's an a value once more of negative 1, and we do get the g of x equals negative f of x as we did on the problem 10 before. Okay, so that's us writing these equations. Now, listen, guys, that was just a single transformation. There are times where we could do a bunch of them. If I gave you an example, I'm going to say this one out loud. Let's say we did the following. We take g of x, and it's a transformation of f of x where we reflect it across the x-axis, stretch it vertically by a factor of 2, stretch it horizontally by a factor of 7, translate it 3 units left and 4 units down. Okay, well, that's what this thing looks like here. That's pretty complex, and everything got inside of there because of the changes. And we can apply all those things to whatever kind of graph it is. I could do it to this graph and flip it over and double it and do all that. You know, that's something that could apply. So just be aware that those things can happen. We'll get kind of a composition of them, if you will, transformations, kind of later down the line. I think that the numbers 15 and 16, they do multiple together, but instead we graph them. We describe it and graph them. All right, so let's move forward, guys. Numbers 13, 14, numbers 13 and 14. This is kind of a new topic, if you will. Determine if each function is an even function, an odd function, or neither. So here's what these things mean. An even function means that if I flip this thing over the y-axis, if I have symmetry across the y-axis, then it's an even function. Sorry, if I flip it over the y-axis and there's symmetry, that I get the same graph out as I did before, then it's called an even function. So you'll see what that looks like when I flip them over. I'll tell you right off the bat whether these are or not. So let's look at number 13 here. I take this graph right here. What if I took this entire graph and I flipped it over the y-axis? You saw me do this before with the reflections. If I take this thing and I flip it over, do I get the same graph out? No. This is not an even function here. Now, I shouldn't say no here, but I'll just say not even, because it might be odd. Not an even function. I flipped it over the y-axis and I didn't get the same graph out. Right here, is this one an even function? If I draw this thing right there, I'm going to go ahead and reflect it across the y-axis. Do I get the same graph out when I flip this thing over? I just flipped it over. The answer is yes. My drawing was pretty rough there. This is definitely an even function, right? The other one was not, but this one is. That's even. Sorry, something just happened to my mouse here. Let me see if I can change that. Give me 1 sec. Let me pause this thing. Okay, I'm back. Sorry about that. All right, now my mouse thing looks normal. Okay, so that one definitely is an even function. Now, I think they do kind of just want us to look at the graph and do this. I'll tell you other ways that you can tell because you can't use the reflection piece. Now, right here, when I take this one and I flip this one over, ask yourself, can this reflect across the y-axis? Does it have symmetry when I do? So I'll take it. I'll flip it over. No, it looks like it's a different thing. So this one's also not even. Now, there is another way of doing this, and we're going to have to calculate them later. So I'm just kind of giving you that idea first. But the real idea is this. If it has symmetry across the y-axis, what happens? That when the y values, that you have the same y value out when you take the opposite of your x values. That means that if I take f of negative x, that the y value that you get here when you change the sign on x is the same as the y value that you get with your original x. That sounds maybe confusing, but let's take a look at some of these graphs again and try and make sense of that. Before, let's say that f of 1 was negative 3. It's close enough, but you have this point 1 comma negative 3. When x is 1, y is negative 3. F of 1 equals negative 3. I know I'm saying the same thing over and over. I'm just making sure that you know that. What if I do f of negative 1? Is the y value negative 3? When I do f of negative 1 on this original, let me get rid of the blue one. On this original graph right here, when I do f of negative 1, is y negative 3? No, it's positive 3 right there. F of negative 1 isn't negative 3, it's positive 3. That doesn't seem to be what an even function does. In an even function, I should get the same y value out, not different ones. It should be down here. That's what's going to give you that, like this right here, what's in green. That would be symmetrical across the y-axis. This would be an even function because you'd get the same y values out when you change the sign of your x value. So it needs symmetry across the y-axis. This doesn't have that. And this one does. If I did f of negative 4, I get 0. If I do f of positive 4, I get 0. If I do f of this, I get that. F of negative this, I get the same y. And that gets an even function that's symmetrical across the y-axis. There are other things that are involved, things that can be even functions, such as they can all have even powers and such. And I don't think I can get too deep into that and misconstrue you, so I won't. Let's consider what an odd function might be, though. An odd function is, it has a different kind of symmetry. It has what's called rotational symmetry, or point. I'm not going to say rotational. I'm not going to deal, but I'm going to rotate it. It has what's called point symmetry. It has point symmetry across the origin. It has symmetry across the origin being that single point. Now, what point symmetry means is that if I rotate an object 180 degrees, I get the same object out. So if I take this drawing here, this number 13, and I rotate everything in this object 180 degrees, do I get the same object out? Remember, 180 degrees around the origin means that around that point right there. So if I take this and if I rotate it 180 degrees like this, do I get the same object out? The answer here is yes, I do. Check that out. I get 180 degree rotation. Boom, I get this thing back out what I had before. Notice how it rotates around the origin. Notice how the origin keeps this point right here when I rotate around and it does that. Pretty cool there. That's what's the point symmetry. Rotational symmetry 180 degrees around the origin. Now, the equivalent of that is that if you rotate something 180 degrees, you might remember these rules when you've transformed other objects. Whatever x, y values you had before, both of their signs change. So in this instance, what that means mathematically is you can't rotate them, is that when you take the opposite of your x value, you end up getting the opposite y value from this x here. When you take the opposite x value, you should get the opposite y value. You go from some xy to some negative x, negative y. You take the opposite of what's there. So when we look at this graph right here, and I do something like f of negative 1, and I get positive 3 or something close to that, when I do f of positive 1, I should get negative 3, and I do. The signs change. F of negative 1 is positive 3, and f of positive 1 is negative 3. This is not an even function. This is an odd function here. Clearly b, although being an even function, it's not an odd function because when I rotate this thing 180 degrees, this would go around this way. It doesn't become the same graph as we had before. When I do f of this value, f of negative 1 or negative 3, I get close to positive 3. If I do f of positive 3, I should be getting like that negative 3-ish over here, and excuse me, I should be getting this, and I'm not. I'm getting that point up there. So this is not an odd function. This one, not quite here. You know, we should be getting the same value. We should be getting the opposite y value out on the other side here. When I do f of negative 1 and I get positive 2, if I do f of positive 1, I should be getting negative 2, and I'm not. I'm not getting that rotational symmetry right here. You can see if I take this one and if I rotate it around 180 degrees, you're going to get a different result of a graph here. Rotate 180 degrees, we get this look. I don't know if that's 180 from there. Yeah, that's 180. So we get this look right there, and that's, you know, that's not what we're getting as a result of that. Sorry, it should be right. I don't know. I don't know if I'm rotating, because I'm not rotating around the origin there. So if you rotate around the origin, you should get something different. But anyway, you're not getting that. Oh, I know what it is. Should look like that. So anyway, so that's not 180 degrees there. It's not the same graph out, and that's not odd. It's not odd. It's not even. It's neither. That's neither odd nor even. Neither. Okay. So that's looking at them with graphs. You can obviously plug in points like I did and say, are we getting the other version of the graph thing out with that on the other side? Number 14, determine whether each quadratic function is an even function. Answer yes or no. Now you might have to show work on these things. So here's once again the thing for even functions. We say symmetry across the y-axis, but I'm not intending on graphing these. All I'm going to say is if I substituted negative x into my function, do I get the equivalent of what I would get with f of x? So f of x is 5x squared. What our hope and goal is that f of negative x is also 5x squared, that I get the same y values out from here. Now, how can you tell we do that? What you do is you substitute negative x in for x. You know, when you substitute something into here, you actually plug it in for x. So f of negative x means I'm going to substitute negative x into this right here, 5 negative x quantity squared. Now, how would you know what this thing is? Well, you know what happens when you square a number? It turns positive. Regardless of what it was, it turns positive. So the opposite of your x squared should become the equivalent of your positive x. So this f of negative x does become 5x squared, because negative x quantity squared is positive x quantity squared. So yes, f of negative x is 5x squared, just like f of x is 5x squared. Yes, this is an even function. You could try and plug in numbers. Let me give you an example. Let's say I substituted 3 into here. F of 3 is 5 times 3 squared. 3 squared is 9. 5 times 9 is 45. F of 3 is 45. When I plug in 3 for x, I get 45 for y. F of negative 3 is 5 times negative 3 quantity squared. Negative 3 squared is also positive 9. Times 5 is also 45. I'm getting the same y value out by substituting the opposite x value in. And that's where you get that symmetry across the y-axis. That's what we're getting. That's what an even function does. All even functions do it. This is an even function. All right, part B. F of x equals x minus 2 quantity squared. We want to check and see if f of negative x will give us the same thing. Will we also get x minus 2 quantity squared? So what I'm going to do here is I'm going to go ahead and substitute negative x into here. Negative x minus 2 quantity squared. And, you know, it depends on what algebra you know from this stuff. I mean, I could tell you right off the bat that already it's not the same thing. This is as simplified as, or you know, it's not simplified here, but squaring this thing doesn't mean I can just square that x and boom, therefore. Remember, when you square a binomial, let me give you the FOIL version of it. Negative x minus 2 times negative x minus 2. You multiply negative x with negative x. Sure, that gets you an x squared. But negative x times negative 2 is positive 2x. And this negative 2 times negative x is positive 2x. Negative 2 times negative 2 is negative 4. So you get x squared plus 4x plus 4. Well, if you do the same thing with this one, you're going to get x squared, x minus 2 times x minus 2. You're going to get x squared minus 4x plus 4. X squared minus 4x plus 4. These are not the same y values that you get out, because if I plug this in, I plug something into x here, I'm going to get something different from here. You can probably tell just by substituting from the very beginning that that didn't simplify to be the other thing. When I plugged it in straight up as you look at it here, it's not equivalent. It's not equivalent there. This one had more simplification room to go where we had to square that negative x. This one I just showed you that when you did it, it didn't work. This is a no. And I know I'm probably over-explaining, but when you get a different problem of a different ilk, I need you, whoever I'm speaking to, I need you to know how to do it. So part C, f of x equals x over 3 quantity squared. F of negative x, that would be negative x over 3 quantity squared. And remember, this can simplify very simply here just by squaring the negative x, squaring the 3. That becomes positive x squared over 9. Now this, when I square this one, I would also get positive x squared over 9. So these things do simplify to the same result there. Yeah, I think it's worth simplifying to determine what's there. You know, you could try and plugging in numbers. You just want to be careful to not get what's called a false positive, which means that two things happened to be at the same height just by pure happenstance, but nothing else would have. But this is a definite yes here as that thing grew. And the last one here, f of x equals x squared plus 6. Well, f of negative x would be negative x quantity squared plus 6. Negative x quantity squared is the same thing as positive x squared because I'm just squaring the x there. I get x squared plus 6 as I simplify. That is the same as that one. That is a yes. So again, we're looking to see that when we substitute a negative x into there, we get the, you get f of x from that. The same thing. You get the same y value out. For odd functions, we would plug in the same thing, and we would try and see if we get the opposite effect, that we get the y value that's opposite it. They didn't ask us to test it, so we're not, but we could have. All right, 2 more problems, and then we're done. Describe how to transform the graph of f of x equals x squared to obtain the graph of the related function g of x, then draw the graph of g of x. So now we're going to take this thing. We're going to use what we did before. Does this copy paste? I'm trying to paste. I already closed it. Let me go back. Let me get our basic equation. It's not very basic looking, but let me get this equation here. Copy. Oh, you didn't copy. Give me one moment and try it again. Copy. Paste. There it is. Okay. So getting this equation right here, guys, we are going to determine, do we have an A, a B, an H, a K, things like that. And then based on that, we can describe what we're doing with it. Are we reflecting? Are we, translating? Things like that. So we have a negative in front of the f of x portion. So that looks like it's in reference to your a value. Looks like our a is going to be some sort of negative value. Is it negative 1? Notice how everything's divided by 3. If I rewrote this thing, I could rewrite it as negative 1/3 times f of x plus 4, like that. Negative 1/3 is the same thing as dividing by 3 there. Negative 3. So right here, your a value is negative 1/3. We can describe something based on a being negative 1/3. If a is negative 1/3, that means that we will reflect this over the x-axis. We'll reflect f of x over the x-axis. I'm not going to bullet point this. I'm going to make this one long sentence. We are going to compress f of x vertically, because it's a, by a factor of 1/3. And then we have the x plus 4 here. Now, if you recall in the equation, it looks like b is unaffected. That's just 1. But we have an x minus h, and this says x plus 4. Well, what would we have to subtract to get a plus here? The answer is we'd have to subtract a negative 4. The h value here, the h value is negative 4. So the last thing we're going to do is we're going to translate this 4 units to the left and translate 4 units to the left. And we do want to do it in that order, as in if you did graph one bit at a time and did this thing, you'd save the translations till the end. You do the compressions and stretches and reflections first. You do the reflection first. Well, you do the compression first, but you do those first, and then you do the translations after. So you want to actually write it in that order. So the a and the b go first, the h and the k do go last. So here's what they want us to do, guys. They did actually give us a function this time, f of x equals x squared. This is our parent function, if you will. This thing is originally graphed like 0 squared is 0, 1 squared is 1, 2 squared is 4, and that's all I can fit on that side. Negative 1 squared is positive 1, negative 2 quantity squared is positive 4, and the original f of x graph looks like this. Well, now we're going to do a couple things to it. They gave us the equation and we came up with the description. And I think based on the description, we can likely create what the g of x graph is supposed to look like based on it. So we're going to do 3 things to this. Now I'm going to do it in a, I'm going to move things around and do things like that probably. We'll see. First, let's reflect this graph over the x-axis. So g of x initially, don't draw this yet unless you plan on erasing. But I'm going to flip everything over the x-axis. 0, 0 stays there. This 1, 1 turns into 1, negative 1 as it flips over. And this 2, 4 turns into 2, negative 4 as it flips over. This thing flips over on this side as well, and we get this thing that looks like that. So this thing is now flipped over the x-axis. But that's not the only thing that happens. What else happens to this thing? Well, this thing also compresses vertically by a factor of 1/3. So this graph ultimately, I can't seem to shrink it on its own. But this graph ultimately here, guys, instead of being this tall downward, it's going to be shrunk. It's going to look more like this right there, right? It's going to be shrunken in like that. And then the final thing they'd ask you to do is they'd ask you to translate this thing 4 units to the left. So ultimately, it's going to go over there, and it's going to be shrunken. Now, I'm going to redraw this all as 1 because I'm going to explain what I like to do with these graphs here. I do like to start with the vertex point. As I said, you translate last. It depends on you understanding that something's still going to flip over and you know what to do with respect to the vertex. So I'm going to start by translating 4 units left myself. I'm going to translate 1, 2, 3, 4 and plot that point. Knowing that it's going to flip over from the vertex, knowing where my vertex is, and knowing that the stretch factor is 1/3, I'm going to take all these points here and I'm going to go ahead and divide them by 3. So instead of over 1, up 1 like the original f of x is, I'm going to reflect it over 1, down 1. But I'm not actually going to go down 1. I'm going to go down 1/3 of 1. And 1/3 of 1 is 1/3. So I'm going to get a point that kind of looks like that. Instead of going over 2, down 4, I'm going to take 1/3 of 4. 4 divided by 3, I use a calculator, it's 1.3 repeating, so negative 1.3 repeating like that. These points aren't that great, and I do apologize, this is the book doing it. By the way, you guys can totally use a table for this stuff. I'll show you a different equivalent of what we can do here based on plugging these things in. I don't know if it's going to be great for you, but you can use it. The last thing is, let me get one more point that I can fit, that I know that really looks good on this one. You know, if I did over 3, I would have gone up 9, because 3 squared is 9, right? So instead of going over 3 down 9, let's go down 1/3 of 9. And 1/3 of 9 is 3. So I'm going to go down 3 to negative 3 right there. And this graph also reflects on this other side right here, and right here like that. So it does continue in that fashion. This is our g of x graph. I know this one probably got a little confusing in comparison to all the other stuff, mostly because you're dealing with the behavior of a graph is x squared. And we haven't really talked about those for a while, but that would be the g of x graph right there after all that stuff occurred. Now, the last thing that I wanted to show is because they actually gave us what f of x was, they said it was x squared. I want to show you this here before I do number 16. If f of x is x squared, and if g of x is negative 1/3 times f of x plus 4, what we're going to do for g of x is I'm going to take f of x being x squared, and I'm going to put x plus 4 in place of it for this g of x thing. So f of x plus 4 is x plus 4 quantity squared, like that. So g of x is going to actually look like this. It's negative 1/3 times x plus 4 quantity squared. And if you know what to do with these parabolas, as in this is your a value, this is the thing, we still do the same stuff, but this is what the actual equation for g of x looks like. This is the actual graph of y equals whatever. That is this actual, like you can go to a graphing calculator. This is the graph you're going to see. And this is the x squared. That's what you're going to see. Okay. Last one, number 16 here. We're still going to be using f of x equals x squared to draw the related function g of x right here. This one looks like it has a b value. Now, this is a little tricky because if you look at the equation, you have to remember that 1 over b looks like it's 2, right? 1 over b is my 2. It's not just b that's 2, but 1 over b is 2. If I multiply both sides by b, then I'm going to get 1 equals 2b. If I divide both sides by 2, I'm going to get b is 1/2. So b being 1/2 is part of the explanation of what we're going to be doing here. There's no reflection because b is not negative, but I am going to compress this thing horizontally by a factor of 1/2. Compress f of x horizontally by a factor of 1/2. So it's going to squish this way. And then I'm also going to, with k being 2, as that plus 2 shows up there, I'm also going to translate this graph 2 units up. Now going back to what f of x was, which is that blue graph, I'm going to go and draw it here one more time. This was 0, 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. I can't really fit it up there. -1, yada, yada, yada. You know, you did this stuff probably in last year if you're looking at this stuff with me right now. This is what the original f of x graph looks like. Now we're going to draw g of x here with respect to f of x given what happens here. Now you know that I like to deal with the vertex first. So translate 2 units up means I can start from this point, translate 2 units up, and everything I'm going to do is in relation to the vertex. So compress by a factor of 1/2 means instead of going over 1 up 1 and over 2 up 4, I'm going to go over 1/2 up 1. So I'm going half the amount that I would before. And instead of going over 2 up 4, I'm going to go over 1 up 4 because I'm compressing that 1/2 there. And I'm going up 4 from my vertex, from 2. That's me considering that. And -1/2, comma 1, -1, comma 4, as we're taking half of 1 and half of 2. And those are the only points I can fit there. So that's the g of x graph right there. That's what that one would end up looking like. Okay, and there's that final result. So anyway, so that's what that graph looks like there. And once again, if I did write the official version of it, this f of 2x plus 2, if f of x is x squared, then f of 2x would be 2x quantity squared, which is 4x squared. You can see how a b value just turned into an a value here. This also means this has a vertical stretch factor of 4. See if that makes sense. Instead of over 1 up 1, it's over 1 up 4. So that's what I was saying. B values don't always exist in that same kind of way, but that's 4x squared. And then there was a plus 2. So if g of x is f of 2x plus 2, we know that f of 2x is 4x squared. That means g of x is 4x squared plus 2. So if you graphed this in a graphing calculator, guys, this is the graph that you'd be seeing right here. That's the graph you'd be seeing right there. Anyway, guys, that's it and that's all. I know that that's a lot that I covered there, and that's all format, but I hope that a lot of this made sense that I described. It probably started to make sense until this final page with the odd even stuff and with the graphs here. I know that some of it can get confusing. Hopefully, as I do more of these kinds of things later down the line, it starts to connect a little bit more as far as what you're actually doing. But that ought to do it for me, guys. This is Mr. Robinson. Thank you so much for tuning in, and take care.